Hi, my name is Justin Pierce, and I'm the lead developer of Iron Software, speaking to you today from our office here in Chiang Mai, Thailand. I'm super excited to be part of the conference. And for the next 30 minutes, we're going to be discussing C++ interoperability within .NET. We're going to be discussing how you may go about using C++ libraries within your .NET library or app. We'll briefly touch on a few basics for those who may not be familiar with C++, and then we'll dive into how and why to utilize native libraries in your .NET solution, as well as a range of common pitfalls you may encounter when calling your native methods from C#. All right. So before we dive into some code, let's look at some use cases for C# C++ interop. .NET offers a lot of conveniences over C++, including automatic memory management, being platform agnostic since .NET Core, and having easy and convenient syntax, including such things as link expressions, interfaces, and more. I think most people would agree that C# probably presents a lower barrier of entry when compared to C++. So that said, in what cases might we want to integrate a C++ library into our C# application? Well, the first case is that just to gain access to the mountain of powerful C++ libraries out there. In some cases, these libraries may only be available in C++, so you'll have to write your own interop wrapper from scratch. In other cases, there may be C# bindings available out there, but you may find them lacking or out of date. Another reason you might want to call native methods from C# is for real-time applications such as robotics or controlling hardware. While low latency applications certainly are possible in .NET, historical precedence kind of favors native code over managed code hardware interaction. Finally, native code offers low-level computer graphics APIs such as OpenGL, Vulkan, and DirectX, and some other APIs that may be specific to your operating system. So before we dive into that, let's make sure we have some native C++ functions available to call from .NET. This portion will assume some basic knowledge of C++. All right. So first off, just be sure that your native assembly has some methods marked for export so that they'll be visible from the C# side. We can accomplish this using the DLL export attribute in C++ or by using module definition file. Next off, you're going to want to make sure to generate a shared library. So DLL.so or .dilib on Mac, and not static library. This one's important. Make special note of your method signature. So, the return type, the parameter types, and of course the method name, because we'll need to declare a matching delegate in C# later on. Finally, ensure your assembly file is discoverable by your C# library application. .NET will be loading your native assemblies at runtime. So we need to be sure to deploy our native assembly along with our .NET application and to place the assembly somewhere that it's easily discoverable. Okay, so let's assume that we have our native C++ assembly compiled and ready to go. How can we approach interacting with our valuable native methods from within .NET? So the approach we're going to use here is called Invoke or platform invoke, which is the bread and butter of C# interoperability with C++. This is a C# technology comprised of some special methods and attributes within the system and system.runtime.interop services namespaces. To p-invoke our native methods from our managed code, we either can use C#'s DLL import attribute or the more flexible native library class. So we'll take a look at these two approaches, starting with the DLL import attribute. All right. So let's look at a couple method signatures which use the DLL import attribute. Our first example is a simple addition function. Not too useful in practice, but a good place to start nonetheless. Notice that on the right in the C# code, when you use the DLL import attribute, you're limited to specifying the assembly name and path at compile time. Our second example demonstrates how to match calling conventions, which can be relevant in specific circumstances, particularly when dealing with multiple platforms, but it's probably not something you'll come across too often. And for the third example, we can see how we might pass some strings over to a native method and retrieve a result of their concatenation. Note that we can't just return a string from C++ back to .NET. And we'll go over this a little bit more later. So the DLL import attribute is still widely used. You'll see it on like a lot of examples and stuff. But nowadays in .NET 4, there's a more modern, flexible option available, and that's with the native library class. So before we start really running some code, I'm going to go ahead and show you the syntax for the native library class. All right, so let's look at the syntax for the native library class available in .NET 4. So in order to use the native library class, first we need to declare a delegate to match our native method, our C++ method. This is just like we went over in the previous slide, except now we use the unmanaged function pointer attribute rather than the DLL import attribute. Second, we want to use the native library class to load our native assembly. Notice how the syntax for this is a bit more flexible than the DLL import attribute, as it allows us to resolve the path at runtime. Once we have the library loaded, finally, we want to retrieve the native function pointer and cast it to our C# delegate. So then we can invoke it elsewhere in our .NET library, just like any other method. So as you can see, this approach requires a little bit more boilerplate code than the previous approach, but it offers greater flexibility. So for me, this is the preferred approach and the approach I will be using for the remainder of this presentation. Okay, let's finally dive into Visual Studio and run some code. We'll be running a simple .NET 8 application, which is going to just call some various interop methods, which we have predefined here. So let's make sure we have the right build configuration selected and go ahead and hit run. All right. So as you can see here, we're able to get through about 5 of our interrupt methods, but then we encounter an exception. So like I said, our first few interrupt methods ran successfully, but then we encountered an exception when trying to invoke a interrupt method called mangling. So why can't our library loader find this method, and what can we learn from this? Well, as the method name implies, the name has been mangled by the compiler. Name mangling is one of the many pitfalls to look out for when implementing C# C++ interoperability. Luckily, there's an easy fix for this. Very briefly, exported C++ method names will be mangled to allow for method overloading, which is just a feature of C++ that allows for methods to share names but have different parameters. On the screen here, you can see the difference between a mangled method name, which is on top, and one that is not mangled on bottom. The reason this particular method name was mangled is because we declared it outside of the scope of our extern C directive. Declaring the method within that directive or specifying the module definition file, like, for example, what you can see here on the screen, will avoid this issue. So in order to avoid this issue, I'll just compile using the build configuration, which includes the module definition file. So let's go ahead and see what that looks like. We'll just change our build configuration to debug in order to build using our module definition file. We'll do a fresh rebuild just to be sure, and then we'll just hit run. All right. So there you go. All of our interrupt methods ran successfully, including our method which previously encountered an error due to the name make issue. Okay. So we've already seen one example of some of the challenges we might face when using interop with our name mangling issue. So what are some other things that we might face? Well, first off, there's memory management. Oftentimes, you may need to pass complex types across the interop boundary. And in these cases, you'll need to keep track of what objects are allocated in .NET and thus managed by .NET's garbage collection, and which objects are allocated in native code. And therefore, you may need to clean those objects up manually when you're done with them. Next is type marshalling. Real world use cases will require custom type marshalling to kind of translate your objects between a type that's compatible with C++, and then into a type that's compatible with .NET, and vice versa. This can increase the complexity of your code and kind of make debugging a bit more difficult. And then there's kind of error handling or exception handling. Unhandled native exceptions are not allowed in interop methods. In other words, it's necessary to catch user exceptions in C++ before they reach the interop boundary. Instead, you can just use a return value to indicate success or failure of your interop method. Okay, and then there's different operating systems and platforms. Since C++ compiles to native machine code, you'll have to compile and deploy a separate native assembly for each unique platform that you wish to support. For example, Windows, Mac, Android, etc. This can greatly increase the complexity of your software, especially in regards to testing and deployment. So for type marshalling, let's go ahead and start with looking at marshalling Unicode strings. Marshalling Unicode strings requires special care when using them as like a parameter to your interop method. As string encoding is often something we kind of take for granted in .NET, as it tends to be taken care of automatically by .NET. However, in C++, that's not the case. So when marshalling Unicode strings, we must be careful to consider potential platform differences. For example, the encoding on Linux may be different than Windows. So there's a few different strategies for handling Unicode strings in interop, and I'll outline one potential strategy. In order to marshal your Unicode compatible strings from C# to C++, we can just get the byte array in .NET and get it encoded as UTF-8, pass that byte array as an interop parameter, and then convert the byte array back to a platform-dependent wide string within C++ using the STV code CVT methods. Okay. So how about marshalling structures? Eventually, as the complexity of your program grows, you may want to start marshalling more complex types. Using structs in your interop methods will help reduce parameter count, reduce boilerplate code, and promote reusability. So some points to remember when marshalling structures. Structs can contain arrays, which should be passed from C# as an int. Structs can also contain other structs, which should also be passed as an int pointer. Keeping struct definition in sync between your C++ header files and your .NET code can require vigilant and defensive coding practices. You may be able to catch layout mismatches between C++ and C# using strategies like hash codes. You can hash the struct and store the code as one of the members, using version numbers, or verifying the struct size on both ends of the interop. When working in a team, consider implementing processes to guard against layout mismatches, such as assigning the code owner to any files which may define struct layout. So far, we've covered how to export methods to C++ so they can be called in .NET, how to call those methods from .NET using either the DLL import attribute or the native library class, and some strategies for marshaling structs and Unicode streams. So these topics will provide you with the basic building blocks for integrating interop into a .NET application. But we're not done yet. Next, we'll cover a few more topics to help you transition your proof of concept into production code. Okay, so let's cover error handling. As I previously mentioned, unhandled C++ exceptions must not be allowed to reach the interop boundary. Doing so will always result in a generic SCH exception, which lacks the original exception message and makes debugging a little bit harder. To remedy this, we can wrap all of our C++ interop methods in try-catch clauses, and then just use the return values of the interop methods to return or to indicate success or failure. We can then check these return values in .NET and then throw a more appropriate error message if necessary. If the return value indicates a failure, we could optionally implement a way to retrieve the original exception information via another interop, if necessary. Okay, so we've got error handling covered, but how do we debug our C++ code when we're running a .NET app? Well, in order to reach breakpoints in native code when executing a .NET app, we must enable native code debugging. And in order to do that, we can just go to our .NET project to Visual Studio and select Properties, navigate to the Debug tab and select Open Debug Launch Profiles UI. And then you'll get this window that you see. And in this Launch Profiles window, you can check the box which says Enable Debugging for Managed and Native Code together. And voila, you can now set breakpoints to C++ and reach them all through the cells. So let's briefly get back into Visual Studio one more time, and let's see what that might look like to hit a breakpoint in our native code. So here I have my console application, and I'm going to navigate over to my interop file here. I have my concat streams interop method, and I'm just going to go ahead and set a breakpoint towards the end of that method, and then run it and see what happens. Okay, as you can see here, we did hit our breakpoint, and we're also able to expect local variables. And on the bottom here, you can also see that we have a valid stack trace that spans both and managed code. Very useful for debug. Note that in order to really see these local variables, you may need to disable optimizations in your C++ project properties. All right. So let's move on to some more advanced code here. You may notice that C# and C++ interop requires quite a bit of boilerplate code, but luckily .NET provides us with the iCustom marshaller interface, which will help enable marshalling of complex types and reduce boilerplate code. So remember that custom struct marshalling we covered earlier? Let's implement a custom marshaller using the iCustom marshaller interface to help streamline the marriage between our .NET class and the native memory pointer, which is passed to the code. Okay. So iCustom marshaller has a few methods that we need to implement, but I'm just going to go over the two main ones. The first one is marshal managed to native, which, as the name implies, is for marshaling your C# classes over to your C++ interop. For my implementation here, we just copy our class values into a struct, and then we retrieve an unmanaged pointer to that struct. Note that we need to be sure to clean up this pointer when we're done using it. For the marshal native to manage implementation, we need to first pass our native pointer to a struct, and then instantiate our class using the values held within that struct. Note that this is a pretty rudimentary implementation, and you can use some other aspects of .NET to make your life easier, such as implementing iDisposable to ensure your unmanaged memory gets cleaned up, or you could use interfaces or implement implicit conversions the cats between your internal interop struct and your publicly exposed class. And going back to what the interop delegate looks like now, we can now see that when we use the iCustom Flare interface, that invoking the interop method looks a lot cleaner, as we just pass the class directly to the interop delegate. Okay. All right. And that's going to be all for C++ interop. Today we covered how you can implement C++ interop into your .NET app using the native library class, some considerations when writing the C++ header files, how to marshal strings and structs, and how to bring your app to production using proper error handling and more advanced type marshaling techniques. A lot of these details regarding interop are things I learned while iterating on our software as the lead developer of Iron PDF at Iron Software. And there's a public GitHub repo with the link on the screen now, available with all the code that I went over today. And I'll go ahead and drop a link to this repo under the YouTube video after it gets posted. I hope some of you find this helpful, and thank you all for your time. Bye.